interesting history. And to some extent, Chadwick experiment was kind of the last step in the history of discovery of neutron. So let me put things which we have already mentioned in kind of framework which I want to underline. So what was the observation? The observation was appearance of very penetrating radiation. Let me denote it N, which was emitted in interactions of alpha particles with light nuclei. It was also lithium, beryllium, and boron, but final experiment was done with beryllium. So alpha particle interacted with beryllium and produced this penetrating radiation. In fact, this alpha particle itself was produced in decay of polonium. Let me put it here. So it's polonium which produced alpha particles. This is important because you can guess what is the energy of alpha particle. And therefore you can use energy momentum conservation to estimate what is the energy of this penetrating radiation. So what was observed is that N has small attenuation when it passes through the materials. So let me put it. So it has weak attenuation. And it is not affected by electromagnetic field, and therefore this should be neutral. So this is the first step which was made by Botte and Becke. The second step was observation that this radiation especially strongly interacting with media which contains protons. And Curie and Joliot, Curie and Curie, so they observed that especially effective interaction of this new radiation with protons. Actually, even now we are using this in atomic reactors. So they use paraffin, which contains big portion of hydrogen. So this unknown radiation interacts with paraffin. And what appeared out of this layer? Protons. So this radiation interacting with paraffin screen or layer eject the protons. So what happens that after all we have protons with certain energy. And actually they already estimated what is the energy of protons produced by this radiation, and it was something like 5 MeVs, but very rough. By that time it was high energy actually, 5 MeVs. So what is the interpretation of this observation? Penetrating radiation, effective interaction with protons. So what is interpretation? the first what you can think about is that this n is just photon. By that time, people didn't know many particles, and especially neutron. The only neutral particle known by that time was photon. And so the first idea which you can get is that probably in this process, the gamma was emitted. The problem is with this appearance of these 5 MeV protons. The point is, and this is so-called recoil energy, this is kinetic energy, or we call recoil also. Recoil energy. So if initial particle is gamma, and then it interacts with proton, and proton is nuclei, as we discussed, of hydrogen, therefore we know what is the mass of the proton. To have this recoil, the energy of gamma should be bigger than 50 MeVs. So, recoil depends not only on the mass of this proton, but it also depends on the mass of the particle which produces recoil. And if you take gamma, which has 0 mass, then one needs to have 50 MeVs, or even more, to produce recoil 5 MeVs for proton. So this is just consequence of energy momentum conservation, right? So conservation of momentum requires that momentum of proton should be equal to momentum of this particle, at least in this direction. And so you can easily find what should be the kinetic energy of the proton with this momentum. And it will be something like 1 MeV only. So this is one point. The second one, that this is too big energy. Typically, in the nuclear processes, in, for instance, decay of polonium, the particles which appear have energies few MeVs. So that was very strange, and it was immediately suspicion that maybe this is not gamma. And one of the people who actually remarked this was Ettore Majorana. Who was saying that, no, this is not gamma, and this is some new particle. So let me make another remark. When we are doing the experiment, as I said, we manipulate with particles. So here, manipulation, in contrast, for instance, from Thomson experiment, when we use electric field, here we put shield and see how this particle actually interacts with this shield. And that was paraffin. And that allows us to explore the properties of the particle. So this is common feature. We have experiment, and we somehow try to affect the particle and to see what is the reaction of the particle. And in this way we restore the properties of this particle. So Chadwick made last step in this discovery, and what Chadwick did, he actually measured quite precisely what are the energies of recoil protons. So it was kind of estimation. But final step was really done by Chadwick when he made measurements of momentum. Well, actually, he had some also information about the angle of scattering, which is also important handle to identify what is this new object. So what Chadwick, and this was third step, was working on, he was working on some detectors of protons and how to explore an energy, measure the energy of the proton. So the overall setup was, let me again remind, it was polonium, which produces alpha. Alpha interacts with beryllium target, produce this unknown radiation, which in turn interacts with paraffin, produces proton, and then what Chadwick added, he added here ionization chamber. That was the key element of his experiment. So that step was done already by Botte and Decay. That was Curie and Joliot added, and now this is what Chadwick did, this part. So what is this chamber? This chamber usually filled in by gas, and when particle enters, it ionizes medium. So protons ionized medium and lost the energy, ionizing atoms. So we will discuss ionization process a bit later. But so what happened is that proton moves and it knocks out the electrons from atoms. And of course it loses the energy and eventually it stops. And so there is an amount of ionization here made. And so this ionization under the electric field is collected onto the plane here. So there is electric signal which was enhanced and then it was measured or seen in the equipments. So what Chadwick did, he explored ionization of induced by the protons. Total ionization depends on initial energy of the proton. And therefore in this way one can really get information about the energy, initial energy of the proton. And so he confirmed and actually measured with quite good accuracy what is the average energy of the protons which appeared in this process, in this chain. And so I will show you probably some slides of the equipment. It was not so big actually, of this size, which Chadwick used. So probably I will mention the following. So proton enters, ionizes, and stops. And usually the distance which is required to stop completely is called range. You can meet this notion. So essentially Chadwick measured the ranges of protons which appeared after interaction with this atom. Then you can use usual kinematics for this process and to find what should be the mass of this particle, since you know also the energy which is released here, to produce a given energy spectrum of proton. So it's kinematics, and first of all he established that the particle should be massive to produce this recoil or energy spectrum. And he established that the mass of this particle should be, as I mentioned already, close to the mass of the proton. And that was already discovered. Because before this, people didn't know about massive neutral particles, elementary particles. Of course, atoms are neutral. And therefore, discovery of any neutral particle with non-zero mass was already discovered. It's easy. It's not like nowadays we have 1,000 particles. And one should still think what you have seen, some new particle or something which has already been known. Well, actually, we will see that mass is a very good identifier of particles. So if you tell me the mass, I will go in to see the tables of elementary particles and immediately find what is this, even not knowing what are other properties of the particles. Only in some specific cases you have so-called degeneracy, when the particles with different properties have the same mass. This is unusual, or if it really exists, that testifies for certain symmetry, which actually is responsible for equalities of the masses. One of the examples is the system of pi mesons. So we have pi 0, pi plus, and pi minus. Still, their masses are slightly different, pi 0 and charged pions. But they are close, and what is behind is so-called isospin symmetry, which we will discuss later. Otherwise, you can immediately, knowing mass, to identify what is the particle behind. So he called this particle a neutron. Questions? So we finished with neutron. So this is the particle which is neutral. It has 0 charge. And mass equals to mass of the proton. It's interesting also that actually here interpretation was very simple. There were just two versions, right? Two possibilities. Either this is gamma or not gamma. And therefore, the only what you need to do is to show that this particle is not gamma. In the present day, when you are doing experiments, actually there are many options, and it's kind of hard time really to select and probably do even some additional experiments to identify really the properties of the particles. So that was the easy in a sense. And Chadwick got a Nobel Prize for this discovery. Questions?
One question. Where does since we know that the mass in this experiment of the neutron is like more or less the mass of the proton, what is the difference mass between the two? Where the other mass that is not there, where does it go?
Right. So that will be essentially our next discussion. We will discuss beta decays, and so what was later observed that neutrons decay. They decay into electron, antineutrino, and they decay into proton. And therefore, knowing what is the energy release in this process, or maximal energy, we will just discuss this after this topic. You can really measure what is the difference of the masses using decay process. I'm looking at this screen, although I should look at this one. Anyway. You see, it's easy to discover, but it's very simple. We discussed the discovery of electron, so it's easy. You see electric field. It's not like the present day experiments, at LHC, when one needs to have several years to make simulations of what you expect to see, right? So that was really very easy. Okay?
Excuse me, Professor. I
Yep.
didn't why you didn't consider gamma.
Sorry?
Why you didn't consider gamma?
Well, we didn't consider gamma because one needs to have two high energies. And then, first of all, which is not released in polonium decay. So in polonium decay, alpha particles have energies few MeVs. And therefore, if it is gamma, the typical energy expected would be that gamma has the energy 5 MeVs, maybe at least 10 MeVs. And this is not enough to produce proton with this energy required. So this is just energy momentum conservation. And remember that the energy, and this is non-relativistic situation, is given by the momentum of proton square over two masses of the proton. So you can easily estimate, since proton was at rest, more or less, so there's a particle with momentum, and therefore in the final state, you have this proton, which has the momentum at most equal to momentum of this gamma, right? And then immediately inserting in this expression, since momentum of proton should be, say, this 5 MeVs, you will get very small energy, kinetic energy, which will be much below than 1 MeV, because this has a big value, right? So this is the first, but then Chadwick measured the energy spectrum, so distribution of the protons over energy. And it was completely out of what you are expecting if you have gamma. Now, if you have massive particle, the energy of this massive particle can be 5 MeVs. Imagine that you have neutron with approximately the same mass as the proton. Then it's enough that this neutron has the energy 5 MeVs because it's heavy. So what can happen then? Neutron hits the proton, stops, and then proton moves. And then the energy will be, just using energy conservation, 5 MeVs. So for a neutron with mass around proton mass, the energy should be not 50 MeVs, but 5 MeVs are enough. Okay? More questions? Okay. So next important particle, next important discovery is discovery of neutrino, or more precisely introduction of neutrino, because discovery of neutrino happened in 50s. Neutrino was introduced or hypothesized by Pauli in 1930, so it's 90 years ago, and he introduced new hypothetical particle to explain paradoxes of beta decay. One should say that in these 30s of last century, people kind of were not acquainted to introduce new particles. These days, you are opening the journal, and every day you see that people introduce some new particles. Well, this is already common stuff, although they may not exist in nature. But anyway, nobody is punished for introduction of some new particles. That time, people were very kind of scared to introduce some new particle. So it was kind of feeling of minimality, and the introduction of new particle was almost like a crime. People even discussed more willingly, say, violation of energy momentum conservation than introduction of new particle. So what are these paradoxes of beta decay? Actually, again, Chadwick studied very carefully and extensively beta decays. And one of the important channels studied at that time was decay of bismuth into polonium plus electron. So this beta decay. The first paradox was related to observations of continuous energy spectrum of electrons. So Chadwick observed many events of this type, and put the distribution, number of events, as function of energy of electron. So for each decay, he measured what is the energy of electron. And what he has observed is the following, the distribution of this type. So actually it was histogram, as usually experimentalists are doing. I'm writing here smooth curve. So why this is paradox? The point is that what you expect from this case is that the energy of electron should be fixed. The energy of electron should be equal, let me put approximately, the difference of masses. We have mass of bismuth minus mass of polonium. If you neglect recoil, so there's still some recoil, there's some motion of polonium in the final state, but you can neglect in the first approximation. You can check again. This is very heavy nuclei. So this is number of nucleons inside this, and you have quite small energy release. And so recoil can be neglected, and therefore the energy of electron should be fixed. And it should be just equal the difference of masses. So one would expect the sharp line in the spectrum and not distributed along the big interval. So this is what is called end point of the spectrum. End point of the spectrum. Maximal energy of electron, which can be emitted. So let me put here, so that's end point of the spectrum. So one would expect just a line at the end point of the spectrum. Instead of this, what has been observed is a continuous spectrum of electrons. Also at that time, people expected that this transition should be lines, like in atomic physics. So it's a quantum process, and you emit something, and it should be some line, like the lines in emission by excited atoms of photons. So this is the first paradox. The second one is related to violation of relation between spin and statistics. Visible violation. So this is the process. And statistics is related to the spin of the system. Bose statistics is when you have integer spin. Fermi statistics, when you have semi-integer. It was also known that statistics is conserved in the processes. I don't want to elaborate more for time being about statistics, because essentially what is behind this paradox is angular momentum conservation in the process, as we understand this now. So it was formulated in this more sophisticated way. What is important that you have, say, you may have integers, total spin in your system, or semi-integer, and this feature should be conserved. Now look at this process. Here, the spin is actually 0 of this nuclei. Spin of polonium is also integer. Actually, you can see this already by this 216. This is even number, right, of nucleons, as we know now. So spins of nuclei were integers, but we have here electron, which has semi-integer spin, and therefore it looks like a system with integer spin, and therefore, obeying the Bose statistics, is transformed into the system with semi-integer spin, which has a Fermi statistics. And that was actually the paradox. So you may say, okay, maybe this relation between spin and statistic doesn't exist, and this system also has Bose statistics. So that was the origin of this name. Now, what is Pauli's hypothesis? And as I said, people actually suggested various interpretations. Even Niels Bohr has suggested the idea that maybe energy is not conserved in this process. So energy is conserved maybe in average. And therefore you have kind of distribution and should not require the exact energy conservation in a given process, in a given decay. Now, what Pauli suggested? Pauli suggested that apart from electron, in the final state, another particle is emitted so that the process is bismuth, go to polonium, plus electron, and plus antineutrino. So I will write already things. Of course, that time he didn't discuss neutrino or antineutrino. It was just some new particle, but I will put correct notations which we are using these days. So this particle should be light, of course, to be able to be emitted and not to change substantially kinematics, and because if particle is heavy, then you would have here end point something like here, right? Actually, this is the idea of present-day experiments to measure neutrino mass. That time, he said that this mass of neutrino should be smaller than the mass of electron. He didn't say about massless neutrinos. He just said that it should be smaller than the mass of electron. Well, it should be neutral. It should be neutral, otherwise we would observe it, or observe the effect of electromagnetic features of this particle. And the most important, it should have spin 1/2. So he called actually this particle a neutron, and then after discovery of Chadwick, of neutron, that was renamed by neutrino. So this immediately explains all the paradoxes and creates new one that we will discuss. So, since we have now two particles in final state, then the energy release, that is the difference of the masses, or what we call QB. So let me use QB, so it's the same. I have deleted already. So this energy release now can be shared between electron and neutrino. So in one event, for instance, Electron takes bigger part of the energy released, and another one neutrino takes, and that actually reproduced the continuous spectrum. For instance, in this point, all the energy is taken by neutrino. And this point, with maximal energy of electron, all the energy taken is taken by electron. And neutrino just keeps very small amount of energy released. Here you have kind of comparable sharing of the energy. So this is the first paradox. Energy release can be shared between neutrino and electron. Now the second paradox is also kind of now trivially solved, because now we have two particles with spin 1/2, and therefore spin of the final state is also integer, right? So the second paradox is solved because we have final state with integer spin. Because spin of neutrino plus spin of electron, something integer, right? It can be 0 or it can be 1. And so there's no problem also with these particles. And of course, because of this neutrality, we do not observe neutrino, it just escapes detection, and so we do not see them. Actually, this is the big problem, which required, say, 20 years or even more to lead to discovery of neutrino. Questions? Well, let me add that these properties of neutrinos, and why people actually were also quite skeptical, not because they also don't like to have some new ad hoc introduced particles, but also it was kind of more subtle question. By that time, people thought that particles which are emitted in decays, they actually were contained already in initial state. For instance, in this process, it was assumed that electron is already existing in this nuclei, and it just released. Now the question is with neutrino. How a neutrino, being neutral, can be kept inside the nuclei? So, new paradox or new question is, how neutrinos, being neutral, is kept in initial nuclei. So that's the main question left after this hypothesis. Do you have answer to this question, by the way? If anyone can make some suggestion. Electron still can be kept, right? Because it has electric charge, and one can guess that maybe electron is just in this bismuth because of electric charge. It's kept by electromagnetic forces. And so in the case of decay, it is just emitted like electrons in atom from envelope from these levels can be emitted. So that was idea. And then in nuclear transitions also, the particle of final state, they are contained in initial state. Any idea how it can be? So the question is clear, right? So we have neutrino in final state emitted. And now where this neutrino comes from, if one says, oh, it was already here in bismuth, then the problem how you can actually keep neutrino in bismuth, because still bismuth has some lifetime, finite lifetime. So why this neutrino immediately didn't escape, since it's neutral and has no also interactions, other interactions. So this question has been answered by Enrico Fermi after he created the first theory of weak interactions. So actually Fermi was saying that this is, for him, is the most beautiful things he invented. And you know, the paper was not published. So not be too discouraged if you think that you have found something really great and the paper is not published. So let me now discuss the Fermi theory. And this is the first step, important step to creation of the standard model. And more precisely, by that time it was the theory of beta decay. So that was created in 1934, 4 years after Pauli hypothesis. And Fermi incorporated two things. The first, discovery of neutron. So let me put here incorporated in his theory. Discovery of neutron, and creation of a model of nuclei which are composed of protons and neutrons. Which was created by Heisenberg and Ivanenko 2 years before. So nuclei are composed of protons and neutrons. The second, he used also Pauli hypothesis. Of neutrino. Very important thing that in construction of this theory of weak interaction, he heavily used analogy with electromagnetic interactions. Actually, this is common trick. So when you start to explain something new, you first try to see, can you use already developed formalism, an existing theory, to explain some new facts? Well, it worked in many, many cases, actually, and I think there's a deep reason for this. So to say, nature likes repetition. So the same kind of laws, the same relations may show up in completely different phenomena. And we know many things of light. So you can find some phenomena in condensed matter and in particle physics and some other places. Although it may happen that there are some modifications. But in general, what you can try first is to use some analogy with what you already know. So let me say a few words about electromagnetic interactions. And these are interactions of photons with charged particles. So, for instance, you have interaction of electron with photon. Gamma, electron, electron. And now let me ask you the question. How many of you know what are Feynman diagrams? Have you seen Feynman diagrams?
Yes.
One. Who else? No one?
Yes, I know.
Two.
Me too.
Okay, three.
Yes.
Four. Good. Don't hesitate, because you know, I will try to do as much as possible to avoid heavily usage of Feynman diagram techniques. So do you understand what is this? So that's, for instance, one. You have electron. So what does it mean? This is the simplest Feynman diagram, if you want, which shows you that you have electron which moves, emits photon, and say again becomes electron. However, momentum may change because you have emission of gamma. So for me, that level would be quite enough. Now, if you have more questions, please tell me, and I can elaborate a little bit more. And you can come to my office, so just send me mail, and we fix the time, and I will discuss this in person. So again, my request is the following. If you don't understand something, or please do this immediately, fix this, because things will be more and more complicated. And then at some point you will just stop to understand what's going on. So please don't kind of move to this situation. So you need to discuss and clarify things as soon as possible. Okay? So this is kind of interaction in electrodynamics. The same can be written for protons when you have interaction coupling of photon with protons and some other particles, charged particles. So here, what we are putting here is the coupling constant. And in the case of electromagnetic interaction, this is electric charge. It can be plus and minus. So this line again shows that we emit photons. Usually we are using straight lines for fermions and these wiggly lines for bosons. The Hamiltonian of interactions is the following. This is the coupling constant. So this is Hamiltonian of electromagnetic interactions. Then psi, this is wave function of field of electron. Then gamma mu, this is gamma matrix. So this is again a function of the field after quantization, and electron and the field which is responsive, which is describing of the photon. And mu is 4 index, so we have 4 gamma matrices, and we have electromagnetic field which has 4 components. So that's Lorentz invariant, because we have here connection of these Lorentz indices. Now what you see here is wave function of electron, and actually that would correspond to this psi. So this is wave function of electron, and this is Dirac conjugate. So that would correspond to this emission. And A mu corresponds to the gamma. So that's the wave function or the field of photons. And this is coupling constant. So this is how we actually treat this diagram. We have these two things. This is emitted electron, this is absorbed electron, and this is emitted or absorbed gamma. Now, this object is called current. Of course, there is a very strict correspondence of what we know in classical physics and in quantum, in many aspects. So, in classical physics, electromagnetic field interacts with currents, or currents can produce electromagnetic field, and here we have the same thing. So we have current, or for current, because we have these indices, which interacts with electromagnetic field, and this is the strength of this interaction, which is, in this case, is electromagnetic coupling constant. Okay? So we called also this as a vector field. Of course, you will have course on electrodynamics, and you will discuss all these things in great details. So we need at least some elements here to develop this course. So in the end of the day, you will understand this better than now, those who didn't work on this before. So this is Hamiltonian, which describes the electromagnetic interactions. Of course, you need to write many other terms. So all the terms with charged particles should be added here. So the term with proton, for instance, etc., with corresponding electric charges. Then we quantize the fields, and when we quantize the field, then that will contain, say, operators of annihilation of photon, that will contain operators of production of electron, that will contain the operators of annihilation of electrons, and then we arrive at this picture. So please ask me questions. Maybe I will need to add one more thing. So this is the lowest process, electromagnetic process. Using this, you can construct more complicated transitions. For instance, scattering of electrons on protons. You have electron and you have proton in initial state. They can exchange by photon. So you see, this is kind of made of two of these vertices, as we have two types of these two interactions. So we have coupling constant here, we have coupling constant here, and so we can compute or get this type of the process, scattering of electrons on protons. You can write also scattering of electrons on electrons. This is elementary vertex. And then you can construct more and more complicated processes. For instance, you can add here also emission of gamma. So that would be the process when you have collision of electron with proton with emission of another photon in final state. And this is process of radiation of the photon. So this type of the diagram corresponds to radiation of photon in the case of scattering of electrons on protons. Okay? Can I move further?
Excuse me, Professor. In this diagram, is this an electron-proton interaction, electromagnetic interaction?
Mm-hmm. Yeah? Yeah, precisely. This is electromagnetic interactions of electron and on the proton. So you haven't studied green functions, right, or propagators in the course of, in the previous courses. Okay. So anyway, I will repeat again and again these things. But for time being, you should just remember that this is elementary process in electrodynamics. Using this, you can cook up more complicated transitions and more complicated processes, which have been observed and very nicely confirmed by experiment. Now let me come to Fermi theory. Well, actually, this is, you know, a difficulty of my course because we will have some problems. We will decide, I will give you problems, and in fact, we will discuss some more complicated things. But I will try to do this without assuming that you know all these type of the techniques. So I hope you will appreciate how I will display the material. So the key point of Fermi theory was that the pair of antineutrino and electron, which appear in the beta decay, this pair does not exist in the initial state. So let me remind that we discussed bismuth, go to polonium, plus electron, plus antineutrino. And these particles in final state did not exist in the initial state. They did not exist in bismuth nuclei. And that resolves the problem with neutrino, how they capture inside the nuclei. This pair, so this is the first step, pair does not exist, but this pair is produced. They are produced by, or emitted by, say, neutron or nuclei or neutron in the initial state, one of the neutrons in bismuth, precisely in the same way as photon is emitted in such a process. So when we consider this process, this transition, we have electron in initial state, which is then transformed into gamma and electron. Of course, it cannot be real because you have no conservation of energy momentum in this case, but it can be virtual photon emitted or electron. So we have this transition, and gamma didn't exist in initial state. It is emitted. So Fermi suggested that electron and antineutrino were also emitted. So let me put here more clearly. So this is electromagnetic interaction. And you have proton, proton, and gamma. In the case of weak interactions, Fermi suggested you have neutron, or one of the neutrons which is in this bismuth, which is transformed into proton, and that actually creates polonium. If one of the neutrons in bismuth is transformed to proton, then you get a polonium. and it emits this pair, neutrino and electron. So here I have gamma, and here I have pair of neutrino and electron. So to say, instead of gamma, I have antineutrino and electron in the case of beta decay, or I need to substitute A mu in the Hamiltonian of electromagnetic interaction by the current, electron, gamma mu, and neutrino. So this system also has spin 1. It's quite similar to what we have for photon, right? So I should just substitute A mu in my Hamiltonian of electromagnetic interaction, this subject. And so I can immediately write what is the Hamiltonian of weak interactions, or responsible for weak interactions. So in the case of electromagnetic, maybe I should write here also. So here the Hamiltonian which is responsible for this process is E, then proton, then gamma mu, proton, and A mu. So this is similar to what I have written before for electron. I have this current, protons current, and then electromagnetic potential, or electromagnetic field. Now I want to substitute this A mu by this object. And I will get the Hamiltonian here, which is P gamma n electron gamma mu nu. And then I need to write here some coupling constant, which is analogy of electromagnetic coupling constant. Usually people are writing this with square root of 2. We will discuss this later. So let me delete this. You see, I used analogy here, right? So I started from this, and this is Hamiltonian for electromagnetic interaction, and this is Hamiltonian for beta decay. So here I have transition of proton to proton. Here I have transition of neutron to proton. Of course, there is some difference, of course. Here I have photon, or field with index mu. Here there is no photon in final state. And I substitute A mu by this current. This is also current, right? So it's current which contains electron production, and this is neutrino absorption or antineutrino production. Plus Hermitian conjugate. Let me put here plus Hermitian conjugate, so which means that it will be another term when neutron will be in this place, proton will be here, neutrino will be here, and electron will be here. Now, look at this Hamiltonian and ask me questions before we'll move further. So it's a great idea. It's a simple step, right? We just use analogy with electromagnetic interactions. Here I substitute photon field by the pair of electron and neutrino. So it's kind of effective photon, if you want, right? Made of electron and neutrino.
Why do we consider, like, why do we have to put or substitute the vector potential in this way? Is there any reason that we do that?
Good question. What we are doing is, first of all, trying the simplest situation, right? the simplest and the minimal, and that works in many cases. The simplest what you can do is do this. And why? Because here we have 4 particles, right, involved. And therefore our Hamiltonian should contain fields of these 4 particles. This is minimal, right? There's no way, so that should be. Now you can add some more particles, but then you need to think what to do with this. Of course, the question, why I put here gamma mu? So, no question that I need here proton, neutron, electron, and neutrino. This is because my process has all these particles. Well, Hamiltonian is what? The sense of Hamiltonian is some energy. Right? And this energy is somehow connected to this interaction. And therefore, all 4 fields should be present. Because if you say, remove this, then it will be something else. Now, question is about this gamma mu. Here, Fermi used just analogy with electromagnetic interactions. He said, okay, you see, I have here gamma mu. Well, actually, this current is kind of similar to this one. So why not to try first gamma mu here? Actually, this is a very big question, because eventually what has been realized that gamma mu is not correct completely. So one needs to add something else here, and we will discuss this later. But as a first tentative attempt is to put just the same gamma mu. You see, that's how the theory is created. We are trying, so this is always trial. So we have this observation of existence, this exists, and we need to describe somehow. So we need to introduce fields. If we are in quantum theory, quantum field theory, we need to introduce fields of these particles involved. It should be product, because otherwise, if one of the fields disappear, then it should not be such an interaction, right? So that's the minimum thing what you can do. So it satisfies condition that one of these fields is not existing, then there's no such an interaction. Open question again, how to organize this. You can actually write like this: proton, neutron, electron, nu. That would be even more simple. You can try this actually. And later, so again, Fermi just used analogy, dot. So let us first do this, which has some good idea, some kind of reason, because again, nature likes to repeat itself. And so why not to try this? What people later did, they actually studied all possible structures. Actually, even this can exist. Actually, it exists when you have, even in the standard model, but it's very strongly suppressed. Let me put it this way. And actually, you can write even more structures. You can put here gamma 5 in addition. You can put here sigma mu nu, which is tensor. This is scalar, what we call scalar interaction, because there is no here indices. Okay, more questions?
I have a question. So, at the time when Fermi wrote this interaction Hamiltonian, what was the interpretation of the A and P? Was it considered as like a combination of creation and annihilation operator, or it was considered as something like a wave function?
No, so look, it depends if you are at quantum level, doing second quantization. If you are do second quantization, sorry, I should add some more. I put here P and that actually, I should write here psi P. Sorry, that I should actually first to say. Or just for simplicity of writing, I omit this psi of the field notation. I'm denoting by the same stuff. So psi in this my formulas is psi P is P, just for simplicity. First, so I'm writing I can write wave functions and consider kind of wave functions. I can write in terms of second quantization. So when I'm doing second quantization, I'm doing the following. So each of these four objects are actually fields, right? So I have field of proton, here I have field of neutron, I have field of electron, I have field of neutrino. Now, in the second quantization, I can actually work a little bit on using classical stuff, or just use immediately wave function. But what we are doing then decomposition of each of these fields in operators of production and annihilation. Okay? Coefficients in front of these are wave functions. So these things are related to some extent. Now, this is the reason why, for instance, this N here describes annihilation of neutron and production of anti-neutron. So again, this is the problem that you haven't studied yet this quantum field theory, and so I'm kind of shorten the discussion. But I'm sorry, I need to really say that this what when I'm writing in this way, this means that it is psi p, or how you denote this, and this is psi p, and this is gamma mu, and then I'm doing this decomposition of the sum, and then over momenta, and then all these things with wave functions, if I do. So I can decompose this in plane waves with corresponding operators of production. But I will not use this technique, because this you will learn in different courses. Good, so.
I have another question.
Mm-hmm.
So I am confused with the symbol so it's like P bar, and when we see like psi bar, it was like psi dagger gamma 0. So are we just considering like it's like the symbol for the creation and annihilation?
So exactly this is this one.
Yeah.
Okay.
But like when we just see also P bar.
Or this one. So that
the Hamiltonian, like in Hamiltonian of the beta decay.
Yeah.
So we have P bar.
Yes, this is the same. So what you have here is psi. If I write this completely, and this will be psi dagger p and gamma 0, exactly. And now this I decompose, and this one is decomposed into production of proton. This is say A p dagger, and annihilation of antiproton. Now, when I use without this Dirac conjugation, that will give me production of antiproton, B. I don't know if you see here. So let me write it here. So I will have Hermitian conjugate terms, which will contain psi p without dagger, and that will be decomposed into operators of production of antiproton and annihilation of proton.
Okay.
Mm-hmm.
Thank you.
More questions? Again, let me repeat, unless I will say something, clarify. Usually writing this, I mean that these are fields or wave functions of the corresponding particles. This is common abbreviation, just to not to have too lengthy formulas.
I have a question, Professor.
Mm-hmm.
In Hamiltonian of Electromagnetics, you said that A mu is like connected with the current,
Mm-hmm.
is contracted with gamma mu.
Mm-hmm.
But here in the second Hamiltonian of beta decay, we have gamma mu is connected with the superconductor, but the electron and the neutrino looks like it doesn't. It's not connected.
is not connected to what? So we have connection here. You have mu here and mu here. I don't know for.
Yes, but the electron and the neutron is connected because gammas are connected, just like that, or it doesn't look like that for me, or is it?
So if this is clear for you, this is current, right? Well, it has 4 components, and actually it's very good analogy to what you have in classical, because 0 component is just density, number density. And vectorial components are V multiplied by N. So that's actually 4 components of current. Now, that's clear, right? You have electron, you have density of the electron. Now, this situation is a little bit more complicated, but again, it is written by analogy. Of course, now I have, this is neutral current. This is what we call neutral current, because there is no electric charge of this object. Here is more sophisticated, because we have neutrino and we have electron. Now you may ask the question, why not I put, say, neutrino here and neutron here? This is your question?
Yes, kind of. I was thinking about that.
No, but again, probably I didn't understand quite well. So we have this one, and we know that in electromagnetic interactions, proton go to proton. Here we have transition of neutron to proton, and therefore I need to write the current which actually transform neutron to proton. Now I have these 2 things, right? Electron and antineutrino. And therefore, I forced to write something like neutrino go to electron or electron go to neutrino, and put gamma mu here to have Lorentz invariance. So this is how it is constructed. Now, what is the physical meaning? It's more complicated thing. I cannot give immediately interpretation in terms of density. I cannot say that, say, 0 component is the density, because here we have both electron and neutrino. Try to ask a question again, but maybe a little bit, because I'm not sure what is really.
No, I get it. I didn't understand well. Now I missed something. This case. I mean, in the first part we can see like a current, in the second too. So.
Well, this is actually also currents, and they are also called charge currents, because this object has electric charge. So this has 0 charge, and this has charge +1, and therefore this is so-called charge current. So I will probably a little bit move further, and then, because there are some clarifications, and then we will come back to the questions. So let me see how much time I have. 10 minutes, okay. So let us now analyze this Hamiltonian in some more details. Well, again, being theoretician, you can try everything what you want. But then you need to check, confront this with observation, experimental data. And if you have some contradiction, then sorry, then you are kind of wrong. If not, then that's fine. So let us discuss properties of the Hamiltonian. First, it's Lorentz invariant, under construction. As it should be, right? So otherwise we will violate Lorentz invariance and we'll have problems. And actually this is why we put here gamma mu and forced to put gamma mu here. Or if we do not put here gamma mu, then it should not be gamma mu here. So it should be some connection of this Lorentz indices. Second, actually this is very important also principle for construction. If you decide to construct your own theory, think about this. Now, this Hamiltonian has structure, current, times current, as product of 2 currents. So we can write this as GF square root of 2. Now, we have hadron current. So these particles like proton, neutron, we will discuss this later, are called hadrons. They have strong interactions. They should have strong interactions because they compose nuclei. Multiplied on so-called leptonic current. Neutrino and electrons, they are leptons. So we can write the Hamiltonian in this way, plus Hermitian conjugate. As we discussed a little bit, it's open question, and let me just underline this again, that in general, you can write your currents as proton, and then here gamma, let me put it here, mu, and here is neutron, and leptonic current as, by the way, here I should put dagger, sorry, let me put here dagger. And this one is electron gamma prime, let me write, and nu. So in general, if you insist on this vector structure, you can write gamma. And gamma actually can be not just this small gamma, but it may be some combination of gamma mu, and here is 1 minus, let me put here, j gamma 5. Right, so I can actually consider two components here. One is just gamma mu, and another one is gamma mu gamma 5. Fermi, again, with analogy and simplicity, an analogy with electrodynamic interactions, assumed that these gamma mu are just gamma. Well, at this point he was wrong. It turned out that what is correct is to write something like this, with gamma 5. So, although he used analogy, the analogy is not complete. And we will see later, so that the current actually not just vector current. So we call this as vector current. In this case, we have vector current. But it contains another component, gamma mu gamma 5, which is called axial vector current. Axial vector current. So the structure of weak interactions, or structure of Hamiltonian responsible for beta decay is the combination of vector and axial vector currents. That eventually leads, and we will see again, to parity violation. So that the presence of this gamma 5 leads to parity violation. Remember, we introduced in the first lecture parity, some feature or property of wave functions with respect to reflection of coordinates. So the idea was that parity is conserved in interactions. So this feature is conserved, and if you have some plus parity in the initial state and parity in the final state is the same. However, what has been found eventually, and this is why we need to write this gamma 5, that parity is violated. And therefore, the currents, true currents of weak interactions, are not just gamma mu or vector current, but they have structure of vector plus axial vector current. Okay? So, next feature is that in the case of weak interactions, they have charge current. So, the currents here are charged. So, proton, neutron, electron, and neutrino, they can be considered in quantum field theory as operators. So you can talk about this operator or this object, and it has charge, and it has charge -1. because here we have conjugations. The proton has electric charge +1, you conjugate, you have -1, and therefore the charge of the current, we can talk about charge of the current, is -1, and the charge of this one is +1, because we have here electron, conjugate, and so we have two charge currents. We have product of two charge currents. Here, of course, the total Hamiltonian is neutral, and this is necessary stuff. Otherwise, we would have processes with violation of electric charge, which you don't want to have. It is not observed. However, each of these components can be charged, and this is what happens in the case of weak interactions. I don't know, so it probably should be 3, right? And now the 4. So what is this G Fermi? There is some difference also here. And the point is that in the case of electromagnetic interactions, E is dimensionless, at least in the system of units which we are using. So the coupling constant is dimensionless. Now here, since we have more complicated structure, so we have 4 fermions. So all these particles are fermions. They have spin 1/2. And each of these fields has certain dimension. Therefore, the question is, what is dimension of G Fermi? How to restore, how to find what is dimension of G Fermi? We know that Hamiltonian has dimension mass to the force. Why? Who knows? This is actually not Hamiltonian, but density of the Hamiltonian. To have total Hamiltonian, we need to make integration. Let me add probably another thing, which I should say this. Okay, I can say this now, and then we will continue. So all 4 fields here are taken in the same space-time point. So that here I need to put this depends on x, this depends on x, this depends on x, and this depends on x. Again, in analogy with electromagnetic interactions, when we are writing electromagnetic interactions as psi, dagger, gamma mu, psi, and electromagnetic field, all these fields should be taken in the same space-time point. So that we have the process like this. And this is the same space-time point for everybody. So they are interacting in the same space-time point. And therefore, all the fields should be taken in the same space-time point. Fermi, in his original theory, of course, suggested analogy, and therefore all 4 fields are taken in the same point. So this is why we are saying this is density of the Hamiltonian. Then the total Hamiltonian will be integration over x. So it's point-like interaction. So that is, everybody is taken in the same point, x. So not only that we are identifying coupling constant here, but also we are saying, writing in this way, that all 4 fields are interacting in the same space-time point. So this means that if n disappears in the point x, then neutrino, electron, and proton should appear in the same point. I will come to this soon in more details. Maybe I will just discuss what is this dimension, and then we will continue next lecture tomorrow. So what is dimension? H has dimension mass to the force. Do you know why it is so?
Because the Hamiltonian has dimension 1 of energy.
Mm-hmm.
Density.
Right, so the point is that Hamiltonian itself has dimension total Hamiltonian, right? It has its energy, and so we are measuring this in energy units, or in the mass is the same. So we have Hamiltonian, density of the Hamiltonian is total, over centimeter cube, so to say, right? In the unit of volume. Now remember we discussed that distances can be measured in inverse of energy units, okay? And therefore we can write this, that this one has the energy or mass dimension, and this has dimension 1 over mass cube. And therefore we arrive at the mass to the 4th power. Right? Now, here we have 4 fermions. So it's 4 fermionic interactions, 4 fermions. So psi, 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 without indices, right? So what is dimension of psi? What is dimension of fermionic field? And how to find this? What is dimension of fermionic field? Sorry?
3
Yeah, why? Yeah, that's true.
Because symmetric term.
Right. Okay, okay. So that's dimension of psi is mass into 3 over 2. And this is because we can write also mass term. That's the same. So again, in our Hamiltonian, we have kinetic terms, which is psi d nu psi. Gamma mu, right? Gamma mu. So this is again has dimension mass to the 4th. This is d over dx, which means that it has dimension mass. So this derivative has dimension of mass. And therefore what we have here, one mass is cancelled from here, then dimension of psi psi equals mass to the cube, right? So because this has dimension mass. This has dimension mass to the 4th, therefore psi, dagger psi has dimension mass cube. And therefore dimension of psi is mass over 3 over 2. Now let's come to our Hamiltonian. Oh, I can probably use this. Yeah. So this guy has dimension mass to the 4th. Now we have 4 fields, and each has dimension 3 over 2, and therefore total dimension in fermionic field is 6. Mass to the 6th, right? It's 3 half over 4 times 4. This means that dimension of G Fermi should be 1 over mass square. Okay? So I think I stop at this point, and tomorrow we will continue with properties of the Hamiltonian. So questions?
Yeah, one question. Since we are talking here also of charged currents, why didn't we use instead of the Dirac adjoint the charge conjugate of the wave of the spin? So
what it will give to you? So usually we are using it for say Dirac particle, this Dirac conjugation. And this is what we are quantizing, and this is what has a physical meaning, right? Eventually. We can try, of course, we can write explicitly psi dagger, but then to add gamma 0 to get some agreement with experimental results and things like that. That you can do, of course. But without this additional gamma 0, you will have already some other problems.
I know, I was talking about charge conjugation of the gamma, of the P of the spinor, because we are talking here about the electric charge production of this.
Yes, so what?
So why don't we use instead of the spinor the charge conjugation of the spinor instead of the bar?
Again, we just use this because that's what appears in quantum electrodynamics. So in quantum you don't want to write gamma zero. This is what you want to say. So if I can write this. This is what you are asking. You have here Dirac conjugate, and you are saying why not to write just this, right? So you want to say, so why not to write here proton like this, and then gamma mu. And this is neutron. That will be different Lorentz structure, actually, this object.
No, that the charge conjugation, not the adjunct.
A charge conjugation. Where you want to have charge conjugation, we have here charge currents. And so because we need to have this object to be neutral. Hold the object. And so we just select in this way so that the product of these two currents should be neutral object. That's uniquely fixed. And if you want to conjugate currents or what? You see, I have written once this equation when I have current conjugate times current. So that, and therefore correspondingly here mu is staying up and here mu is staying down. So that you can write Hamiltonian in this way, of course, this what, and precisely this dagger changes the electric charge of the current, because one current has charge +1, and then this one has charge -1, charge conjugation. Maybe I'm not capturing your question exactly.
No, it's not.
Yeah? Some more questions? Okay, so then it's the end for today, and tomorrow we will continue with this current, and then we'll discuss other issues. Okay, see you tomorrow.